Swayam Prabha. Digital India. Educated India.
So, here is the next example problem. 200 kilograms per hour of an aqueous solution containing 20 mole percent sodium acetate enters an evaporative crystallizer at 60 degrees Celsius. When the solution is exposed to the low pressure in the evaporator, 16.9% of the water evaporates, concentrating the remaining solution and causing crystals of sodium acetate trihydrate to form. The product is an equilibrium mixture of crystals and a saturated aqueous solution containing 15.4 mole percent of sodium acetate. The effluents, which are the crystals, solutions and water vapor, are all at 50 degrees Celsius. Calculate the feed rate to the crystallizer at in kilomoles per hour and calculate the production rate is as kilograms per hour of trihydrate crystals and mass flow rate of liquid solution in which the crystals are suspended. Estimate the rate at which heat must be transferred to or from the crystallizer. You need to also state whether heat needs to be supplied or removed. Now, let us look at how we would solve this problem. First, we need to perform the required material balances. For performing the required material balances, we need to identify the basis. What would be the basis for this system? We have been told that 200 kilograms per hour of feed solution enters. So, the basis for this process would be 200 kilograms per hour of feed solution. Now, let us draw the flow chart. So, you have a process where 200 kilograms per hour at 60 degrees Celsius is coming in. So, this contains 0.2 mole fraction of A per mole of the mixture and the rest is 0.8 moles of water per mole of the mixture. A is the sodium acetate. So, from here you have two streams which are leaving. One is the product slurry. Product slurry is leaving at 50 degrees Celsius and you have two things in this slurry. You have crystals which are present, which are the trihydrate crystals, and you have a solution which is accompanying the crystals. So, we will have A3H2O crystals which are leaving us, and you also have a solution, aqueous solution, which is containing the sodium acetate and water. So, we know that molar composition of this is 0.154 moles of A per mole of solution and 0.846 moles of water per mole of solution. So, the other stream is the water vapor. So, you have water vapor which is leaving the system also at 50 degrees Celsius, and it has been told that 16.9% of water in feed is actually getting evaporated and leaving through this stream. So, let us first label this flow chart and identify the parameters which need to be calculated. So, we have mass flow rate, however, we need molar flow rate because all the compositions are given in terms of mole fractions or mole percentages. So, let us call this N naught kilomoles per hour of feed which is coming in, and we will call N1 kilomoles of water per hour which is water vapor that is leaving the system, and we will also have N2 dot kilomoles of the trihydrate crystals leaving, and we will have this solution as N3 dot. So, we need to calculate all these parameters, which we can do by using simple material balance. The first part of the problem asks us to calculate the molar flow rate of the feed. So, that would mean we would have to calculate, we would have to convert this 200 kilograms per hour into kilomoles per hour, which is N naught dot. Let us try and do this. So, for this we can calculate the average molecular weight of the mixture, which would be 0.2 times molecular weight of sodium acetate plus 0.8 times molecular weight of water. So, this would be 0.2 times 82 plus 0.8 times 18, giving a value of 30.8 kilograms per kilomole. So, this is the average molecular weight for the mixture. So, the molar flow rate N naught can be calculated as 200 kilograms per hour divided by molecular weight, which would be 1 by 30.8 kilomoles per kilogram. So, kilogram gets cancelled and you would end up with 6.49 kilomoles per hour. So, this is the molar flow rate of the feed which is entering the system. So, this is the first part. Now, for the second part we would have to perform material balance calculations. The first information we have from the problem is 16.9% of water evaporates. So, this implies 0.169 times 0.8 times 6.49 would be the number of moles of water which is evaporated. So, this would be equal to N1 dot. So, N1 dot would be equal to 0.877 kilomoles of water vapor per hour. So, then we can write the sodium acetate balance. Sodium acetate balance would be input minus output plus generation minus consumption equals accumulation. It is not taking part in any reaction. So, generation and consumption go to 0 and at steady state accumulation goes to 0, giving you only input equals output. So, there are two components of sodium acetate which are leaving the system and there is only one component of sodium acetate entering the system. The component entering, which is input, would be equal to 0.2 times 6.49. This is the number of kilomoles of sodium acetate entering the system. We now have to identify how many moles of kilomoles of sodium acetate is leaving the system in terms of crystals and how much is leaving along with the solution. So, we have two components, which is the N2 dot and N3 dot. So, N2 dot represents the number of moles of crystal which is leaving. So, that is, we will call that N2 dot is the crystals and N3 dot is the number of moles of the solution which contains the sodium acetate. So, we have also calculated that the sodium acetate concentration in the solution is 0.154 mole fraction. So, substituting these values, we would have the balance equation become 0.2 times 6.49 equals N2 dot plus 0.154 N3 dot. Similarly, we can write a balance equation for water. So, the water balance would also be input equals output. So, water is coming in through the solution and it is leaving as part of the solution, as part of the water vapor and also as water of hydration. So, we need to account for all the three components. We have already calculated the amount of water leaving as vapor, we know the amount of water which is entering, we just need to now write the balance equation for the other two. So, let us write this equation. So, water inlet would be 0.8 times 6.49 and water outlet would be 0.877 kilomoles, which is leaving as water vapor, plus 3 times N2 moles of the crystals, because for every mole of the crystal which is leaving, 3 moles of water is accompanying with it. So, that would mean 3 times N2 would be the number of moles of water leaving with N2 moles of the crystals which is leaving. So, for the water which is leaving along with the solution, we would have it as 0.846 times N3, where 0.846 is the mole fraction of water in the solution. So, now we have an equation which simplifies to 3N2 plus 0.846 N3 equals 4.315. So, we already had an equation where it was N2 plus 0.154 N3 equals 1.3. So, using these two equations we can solve for N2 and N3 when we solve this equation simultaneously. So, N2 would be equal to 1.13 kilomoles per hour and N3 would be equal to 1.095 kilomoles per hour. We have been asked to calculate the mass of the crystals and the solution which is accompanying the crystals. So, we can convert these to masses by using the molecular weight. So, the molecular weight of the crystal would be 136 kilograms per kilomole, because we have 3 moles of water along with 1 mole of acetic acid. Molecular weight of sodium acetate is 82 and molecular weight of water is 18, giving us the molecular weight of the sodium acetate crystals, which are the trihydrate crystals, as 136. So, using that we can calculate this to be weighing 154 kilograms per hour, and the solution would basically weigh 30 kilograms per hour. So, this gives us the flow rates, mass flow rates of the solution and the crystals which are leaving the system. So, the solution would contain sodium acetate and water, and based on the mass fractions we can actually convert the find the average molecular weight and use that for calculating the mass of the crystal solution which is leaving the system. So, these values give us the total mass of the components which is leaving the system. So, you would have the rest of it leaving as water vapor. So, that would give us the total balance for the mass. So, with this we can move on to the next part, which is the energy balance associated with solutions. So, as I have always established, it is important that we understand the first step of any energy balance is material balance. That is why I keep doing problems where I spend quite a lot of time trying to do the material balance before I start the energy balance. So, most of the times in real life scenario, when you actually perform energy balances, the flow rates and masses will not be directly given. So, instead you would have to perform all the calculations required to complete the material balance and then identify the energy balance problem. So, let us do that. The second part where the third part where we are doing the energy balances will be starting here. For the third part, we have been asked to calculate the amount of heat that needs to be supplied or removed from the system. So, let us do that. So, how would we go about doing this? So, first thing is to identify the reference states. The reference states for the two different chemical entities which are present are sodium acetate and water. So, sodium acetate solid at 25 degrees Celsius and water liquid at 25 degrees Celsius can be used as the reference states for our calculations. So, here I am going to slightly deviate from what we have been doing till now. Until now we have been building enthalpy tables. So, this has been simple to use because the enthalpy we get would always be either in terms of per mole or kilojoules per mole of a substance or kilojoules per mole of a solute and so on. However, here we have different solutions and we cannot use one term that can be multiplied with the specific enthalpy. So, we need to look at the process in a more comprehensive fashion. So, let us look at the individual components and try to identify the change in enthalpy for the individual components. The first component we have in the system is the feed solution. So, let us start with identifying the change in enthalpy for the feed solution. So, the change in enthalpy for the feed solution can be N H cap, or so can just be called as H1, and let us, this would be equal to Na times delta Hs cap at 25 degrees Celsius, which is the number of moles of sodium acetate times the heat of solution associated with converting these solid and liquid water, so solid sodium acetate and liquid water pure components into aqueous solution. So, this would be the first component, and this particular solution is then heated to form a 60 degree temperature, to reach 60 degrees temperatures. So, the Cp value for the solution, feed solution and the product solution have been given as 3.5 kilojoules per kilogram degree Celsius. So, we will multiply it with the mass of the solution, which is m integral 25 to 60 Cp dt. So, you would have this become 0.2 times 6.49, which is the number of moles of sodium acetate in the solution, times the heat of solution, which is given as minus 1.71 times 10 power 4 kilojoules per kilomole of sodium acetate. So, that is why we are using the number of moles of sodium acetate here. So, this times minus 1.71 times 10 power 4. So, this would be the first term, and the second term becomes 200 times 3.5 times 60 minus 25. So, this can actually be simplified to get the final value as roughly 2300 kilojoules per hour. So, this is the change in enthalpy for the feed solution. We now need to identify such change in enthalpy for the other components in the process. So, let us look at the next component, which is the product solution. For the product solution, we can again we would have to calculate the change in enthalpy, let us call it H2, as Na times delta Hs cap at 25 degrees Celsius, which is the first step where the pure components are converted into the solution at 25 degrees Celsius, and from here it would have to be heated to 50 degrees Celsius. So, it will be m Cp dt, m integral Cp dt, where it is m going from 25 to 50 Cp dt. The Cp for all the solutions has been given as 3.5 kilojoules per kilogram. So, we will write this, and this would give us 0.154 times 1.095, which is the number of moles of sodium acetate in the product solution, times the heat of solution, which is minus 1.71 times 10 power 4 plus 30 times 3.5 times 50 minus 25. So, 30 is the mass of the product solution leaving the system. So, this will give you a value of H2 equals minus 259 kilojoules per hour. So, the next component we have to look at are the crystals. So, for the crystals, you have the pure components, which are liquid water and solid sodium acetate forming trihydrate crystals. So, the first step is the hydration process itself. So, we have the heat of hydration given. So, we will account for that as the first step. The first step is, so for H3 would be equal to Na times delta H cap of hydration. So, the value is given here, H cap for hydration is given in terms of per kilomole of sodium acetate. So, that is why we have to use the number of moles of sodium acetate to be multiplied with the specific enthalpy to get the actual enthalpy value, plus m integral Cp dt, where the hydrate crystals are heated from 25 degrees Celsius to 50 degrees Celsius, and this would be number of moles of sodium acetate in the crystals which is leaving would be 1.13 kilomoles times the enthalpy of hydration, which is minus 3.66 times 10 power 4 plus the mass flow rate of the stream of crystals, which is 154 times Cp of the crystals, which is given as 1.2 times the change in temperature, which is 50 to 25, 50 minus 25. So, this would mean H3 would be equal to minus 36700 kilojoules per hour. So, the last component which we need to account for is water vapor at 50 degrees Celsius. So, the H4 for that, the change in enthalpy for that would be N, which is the number of moles of water, times delta H cap V, which is the heat of vaporization at 25 degrees Celsius for water, plus integral Cp dt 25 to 50 Cp of water vapor dt, and using this equation we can get these values for the heat of vaporization at 25 degrees from the steam tables and the Cp value for water vapor from any handbook or textbook. Using these values, we would have this become 0.877 times 4.39 times 10 power 4 plus 32.4 times 50 minus 25, and this would be equal to 39,200 kilojoules per hour. So, now the energy balance equation we have would be Q minus Ws equals delta H plus delta Ek plus delta Ep. So, Ek, Ep and Ws will go to 0. So, Q would be equals to delta H. So, which would be equal to the summation of all these three, which is all these enthalpies, which would be H1, H2, H3 and H4, giving Q as minus 60 kilojoules per hour. So, this means heat needs to be removed from the system for the process to happen. That is why you have a negative sign. The heat needs to be removed at a rate of 60 kilojoules per hour. So, with this we have performed an energy balance calculation for a process where there is solutions. Thank you and see you in the next lecture.